So we now see a symmetry between the behavior of magnetic and electric fields. A changing magnetic field, as we've established, induces, first of all, current in a circuit, which we then infer is from an EMF, which is associated with an electric field. It's ultimately the electric field that drives the charges. And so the changing magnetic field induces an electric field. And it can do it in the absence of any charges. There don't have to be charges there to be moved. It happens in space. It happens in vacuum. And we've also just now learned that a changing electric field can also induce a magnetic field in the absence of charges. So there's this symmetry. So consider the following. If in free space we see a changing electric field, which can induce, therefore, a magnetic field, and this magnetic field itself is changing, and therefore it can induce an electric field, since it also changes in time. Thus, a changing E can induce B, which induces E, which induces B, etc., ad infinitum. And this is basically the idea behind an electromagnetic wave. The fields continuously reproduce each other. The fields are continuously recreated through this process we call electromagnetic induction. And when a disturbance is first initiated, a changing electric field, for example, what happens is the electric and magnetic fields sustain themselves and move away in the form of an electromagnetic wave. The analogy I'm going to give you here, which I think is a good one, is the surface of a pond. The surface of a pond is like the field, like the electromagnetic field. And if I poke my finger into that pond, it's going to produce an outward moving ripple or wave. That outward wave is going to move out from the point of disturbance at a particular speed. My finger is like the disturbance which changes the surface of the water. And if you think of that as, for example, the electric field, if I push my finger into the water, it produces a change in that surface which moves outward as a ripple that moves in all directions out from that center point. The ripples can be thought of as the electric field, and the movement of the ripples as the velocity at which that electromagnetic wave moves. So in the case of an electric field, and you might ask, how can I actually produce a changing electric field? If I grasp hold of an electric charge and I shake it up and down in rapid motion, that changing electric field in the region around that charge, the charge produces an electric field, and the changing electric field in the vicinity of that charge then induces magnetic fields, which induce electric fields, which induce magnetic fields, and therefore moves away. The changing fields move away from that point in the form of an electromagnetic wave. So if I shake that charge, I'm producing a changing electric field in that region of space, and that changing electric field produces the magnetic field, and the two form an electromagnetic wave. So the electromagnetic wave is transverse in the following sense. It's a transverse wave. This is a beautiful picture of what's going on here. This diagram shows on an XYZ axis what we might imagine happening. The electric field, first of all, changes. It rises and falls, which induces a magnetic field, which induces an electric field, which induces a magnetic field, and so forth. So as these two fields, the electric field, which is directed along the y-axis, and the magnetic field, which is induced by the electric, and it ends up pointing along the z-axis, are both perpendicular to the velocity vector. This is called a transverse wave because the thing that's waving, the electric field, is moving in a direction perpendicular to the direction of motion. As is the magnetic field, it also is moving perpendicular to the velocity vector. So both the electric and the magnetic fields are perpendicular to the velocity vector. This is what constitutes a transverse wave. We also have found out over time that the velocity of that wave is 1 over the square root of epsilon naught mu naught. These are both electrostatic and magnetostatic constants of space. And they had to do with electromagnetic phenomena. But James Clerk Maxwell was the one that discovered that the velocity of this wave, this E inducing B, which induces E, which induces B, etc., and moves away at a velocity v, he calculated the velocity v to be 1 over the square root of epsilon naught mu naught. If you plug in the values for those two constants, you end up getting something that is a very peculiar velocity, and that is the speed of light. Maxwell immediately noticed that when he calculated the speed of these electric and magnetic waves, he came up with the speed of light. And so he was the first then to conclude that light is actually an electromagnetic wave phenomena. This was quite an epiphany for him. Today we somewhat take it for granted, but when it was first discovered, it was a big deal. That electric and magnetic fields, which we can see in the laboratory, have this dynamic behavior that when one of them changes, it induces another, and a light wave moves outward. That light wave may not have a wavelength that we can see. It's only when charges oscillate at around 5 times 10 to the 15 hertz, which is a very, very high frequency, are waves produced that we can actually see as light. When I shake my charge in space to produce an electromagnetic wave, I can't shake it more than about 4 or 5 times per second, which means that the frequency of the wave that moves away is going to be about 4 or 5 hertz, which is way too low for anybody to see. It constitutes a very long wavelength radio wave. We'll learn more about that later. At any rate, this is now a transverse wave that's produced by this induction phenomena governed by Faraday's law. And James Clerk Maxwell was the one that was able to put together the fact that this electromagnetic wave is actually a form of light, and it moves at the speed 3 times 10 to the 8th meters per second. Another feature of electromagnetic waves that we want to establish is that the ratio of the electric field strength to the magnetic field strength is equal to the speed of light, so that the electric field is about c times the magnetic field b. And c is a very big number, so the electric field is actually a lot larger in strength than the magnetic field in an electromagnetic wave. We also learned, with regard to our study of waves earlier, this would have been last semester, that if we have a wavelength and a frequency for a wave, the product of the two gives the velocity. The velocity is equal to the wavelength times the frequency. For electromagnetic waves, this formula then translates into the formula C is equal to lambda f. In other words, the wavelength and frequency of a light wave will have a product which is equal to the speed of light. So they are linked to one another.